Okay, so like I said, these are the 6 that we're going to do over the next 2 days. We're going to try to get through 3 today and then get through 3 tomorrow. And you'll notice there's a lot of different types of these questions. So the 3 that well, 2 of the ones we're doing today are sort of similar. And they're all involving kind of area or measurements, that kind of stuff, area, surface area, volume. And then a couple of the ones we do tomorrow are quite different. And so this, to me, really is a matter of identifying the type, like knowing how to do all the different types. Okay? There are general strategies or a general format for all of them. But we're going to do these things that I call river questions. And they're very different from these measurement questions, the way that you set it up. Okay, so there are general strategies that remain the same. So you got to get that part of it. And then there are differences in other parts of the setup depending on the type of question it is that you also have to figure out. Okay, so here we go with the first one. Notice that the first one has to do with fencing and with area of a yard or something like that. Okay, farmer has 1,600 meters of fencing with which to create 3 identical rectangular fields. But one side of each field doesn't need to be fenced because it's up against a river. I don't know what this fence is going to be good for, but anyway. Find the dimensions of the field that will maximize area. So this unit is called max and min. And what we did yesterday was finding maximum values of functions. So you'll notice all of these questions that we do over the next 2 days are about maximizing or minimizing something. Okay, so that's one first important part. Probably the first thing you're going to do, and one of the key strategies for getting started in these kinds of questions, is to draw a diagram. Okay, so let's go ahead and do it. Here's my water. Here's my fencing. Three identical rectangular fields. So that means I've got to cut this into 3 parts. We okay with that? Okay, and for these to be identical, obviously these lengths all have to be the same. You don't have to label that, but. Okay, we're going to label one of these sides as x, which means every one of these sides is x. You've done questions like this in grade 10? Yeah, so it's familiar. Okay. And now what?
Could you classify the other side as y?
Okay, you could. The entire side? Mm-hmm. And then we would just have to come up with what y equals. So yep, you could. Something else you might see people do, I don't know if it'll be in the solutions, but it probably used to be, or you might see somebody else do it where they label each of these little ones as y, and that will work. I'm going to do it a different way. So what would y equal?
1,600 minus 4x.
Very nice. So if you label it as y, then you're just going to figure out 1,600 minus 4x. But in this case, we don't really even need the y. Like it's not gonna help us. Okay. So that gives us the last side. And that ensures that we used the 1,600 meters of fencing. So step number 1, draw a diagram. This defines your variables. if for some reason you didn't draw a diagram, like you're terrible at drawing, like a couple of the drawings we do are trickier. If for some reason you can't do that, then you need let statements to define your variables. But this diagram defines x for us. Okay? So I suppose it's one or the other, but diagrams are strongly recommended because it's going to help you visualize and it's going to help you set it up properly. Everybody okay? Step number 2 is you're going to state what you are maximizing or minimizing. So what are we maximizing or minimizing? Thank you. It's in the question. Maximize area. Step number 3. Now this is new. This part you haven't done before. We're going to define the domain of x. What's the smallest realistic value that x could be? 0. What's the biggest?
400.
Why?
Because if you go over that, then y will be negative.
Very good. So this has a lower bound and an upper bound, because if I put 400 into this equation, I get 0. Okay, so I've defined my domain. And this is like similar to the intervals that we were working with yesterday. Right? You had an interval on which you were working with your function. And this makes sense. In fact, we may have talked about this in MHF, we certainly did as well, where like when we're modeling something that happens in the real world with a mathematical equation, the equation only fits that model for a certain amount of time. When a ball flies in the air or an eraser flies in the air, it follows a quadratic path until it hits the ground, right? So and then it's not quadratic anymore. It's just sitting there. So this makes sense that when we are going to come up with a function to model what's happening here, but that function only applies to x within those values, lower bound to upper bound. Does that make sense? Okay, so we're maximizing area. We're in there. Now we're going to come up with our equation in one variable. Sometimes you might have two variables, x and y. How would I find, if I was using the y like was suggested, how would I find the area of this? Length times width. And my width is x and my length is y. So it would be area equals x, y. And every one of the different types of questions that we look at will have a different way that we're setting up this equation, right? Now, but I have to set up an equation in a single variable. I can't have two variables. This is not linear systems or anything like that. So I've got to do this. And when that happens, I'm actually going to define it as a function a at x. So if you start with two variables, that's fine. You're going to eventually narrow it down to one variable, and when you do that, you're going to use function notation. Now what do you think we do? See if you can come up with it. Think about it.
Derivative.
Take the derivative. Why?
It's calculus.
Very good answer. But also, what is the derivative going to tell us?
Where the maximum is?
Like we did yesterday, where the max and mins are, right? So absolutely, we're going to take the derivative. What do you think we should do before we take it? This is product rule? Yeah. What do we do first? Expand. That's going to be a lot easier, right? So again, all of our skills in being efficient and whether we simplify first before taking the derivative or not. But that's good. Now we're going to take the derivative. Factor out the 8. Now what? Zara?
You find where it equals 0 and then do the whole thing to find if it's max.
Or,
Or if it's maxes.
right. So max and mins occur where it's equal to 0 or does not exist. So I'm going to write down that same sentence we did yesterday for critical values. A prime at x equals 0 or does not exist. A prime is a polynomial, so it exists everywhere. So when x equals 200, we have where the derivative equals 0. Remember when I said in calculus, when in doubt, take the derivatives and set it equal to 0? There you go, right? Sometimes you're going to have to actually set it equal to 0 and solve. This one's nicely factored, so we can just see what the solution is. Sometimes we're going to have to do some work to solve. Again, that might just take some getting used to. What's next? Classify. Do we have to? Well, I don't know. What do you think, Nasir? Why?
Because you already know that x is a quadratic with a negative reflection. So you know it's already has an x.
Okay, so we will be allowed to use all the things we know about functions for this process. So what Nasir said is, this is the function a is a quadratic with a negative leading coefficient, so it opens down. So we know it has a maximum. And we know it has a turning point. Like, it's not a twist. Like, what could happen? What are the cases that could happen when the derivative is equal to 0? It's either a smooth turning point, max or min, or a horizontal tangent line, horizontal twist. It's not a twist. This is not cubic. It's quadratic. So we know that it is just the maximum. So a couple things to say about this. If you didn't know whether it was a max or a min, or if you came up with multiple solutions that are all within your domain, your defined domain, you would have to do a check and see which one's right, which one's the one you're looking for. Like, you would have to do the little chart that we did yesterday. If you have time on a test, maybe you just want to check and see that you've done it correctly and you haven't missed something. What would that look like? Well, I would sub in something a prime at 199, a prime at 200. I'm not actually going to set it up as the table that we were doing. I'm just going to set it up this way. A prime at 201. So a prime at 200 is 0. A prime at 201 is 1600 minus 8 times, what did I say, 201? I'll do that one first. So negative 8, so this is negative. And a prime at negative 199. Well, I don't actually need to sub it in. I can just do it by inspection. I'm looking at this line right here, 1600 minus 8x. So if I'm at 199, 8 times 199 is less than 1600. So that one's going to be positive. So it goes from positive to 0 to negative. So it is indeed a turning point maximum. So you can do that if you have time. It's not a bad idea. It's not necessarily required. Okay? And there are lots of cases where you might no other things about the function, and you wouldn't have to do that. You just know it has a maximum. Okay? So I think this one's done. Let's make sure we answer the question. Find the dimensions of the field. So if x equals 200, then y equals 1600 minus 4 times 200. That's 800. Okay, and there's your solution. So what were the different parts that we did? We did a diagram. We stated what was being maximized and defined our domain. We set up and simplified our function or our expression, our model of the situation. We took the derivative and may or may not clean it up. Sometimes it'll factor nicely, sometimes it won't, and it doesn't matter. Okay, we looked at where it does not exist and where it's equal to 0. And then our final answer. Any questions? No, are we sure? Okay, let's see the next one. A box with an open top is to be made from a square piece of cardboard of side lengths 100 by cutting a square from each corner and then folding up the sides. Find the dimensions of the box of largest volume. You got to picture what this one is talking about. Okay, so first of all, I'm going to attempt to draw a square. Actually, maybe can I do a square with this one? Maybe I'll do that. Oh, beautiful. Does that look like a square? Close enough. Oops. Okay, so I've got a square piece of cardboard. How do you turn this into a box by cutting out the corners? Can you visualize that? Some of the artsy people in here maybe can, I don't know, or if you're just a visual person. Okay, but think about it. If I cut corners, okay, so first of all, this is 100. And this is 100. So I'm cutting the corners off. Now visualize this thing looks a bit like a cross, and the flaps fold up together to form a corner. So where's my X? Is that right? So it's going to be all of these lengths, isn't it? Because these have to be the same, otherwise the flaps are different lengths and they won't line up. You can't fold up different lengths to meet. You got to fold up the same. So every single one of these corners is going to be X, 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 X. You don't have to put it necessarily on every corner, but why not? Now let me see if I can draw this again. This is one where you might want to draw it again. But this one's harder to draw for some people, like me. Okay. So now you can see how this flap here was this space, wasn't it? That folded up. Do you see how that works? You draw kind of a diamond. Draw straight down. Same length straight down on all these corners. And then connect them. And like try to make the ones that go straight down be more or less the same length. I don't need your drawings to necessarily look fantastic. For this one, if all you drew was the top diagram, that would be good enough. You may want to draw the second one to label it to visualize. Where's the X in this one? It's this. It's the height of the box. Right? Okay, so what am I missing in my diagram? Nasir? The base width. So this. What is that in the top diagram? Okay, so it's 100 minus 2x. Nice. 100 minus 2x, and it goes from here to here, right? Okay, very nice. Is that okay? I mean, the nice thing is this is one of the types that we do. So like when you do this question again, the numbers will be different. The idea is going to be exactly the same thing, right? So it's not so bad. Once you see the cutting out the corners type, you know hopefully what it's supposed to look like. Okay, so I think that's fully labeled. I think that's pretty good. What's our next step? And what are we maximizing? Find the dimensions of the box of largest volume. So we are maximizing volume. Why do we state what we're maximizing? Because now I know I have to come up with a formula that says V equals, right? Like if I'm maximizing volume, my equation's got to be for volume. So it gives us a focus of what we're trying to set up an equation for. What's our next step? Define the domain. What's the smallest that x could be? Smallest. So less than 50, but so that's the biggest. You got the upper bound. What's the smallest? Somebody said it, 0. So 0, less than x, less than, and we're going to go with 50. You're right, at 50 would make it not a box. Why? Because 100 minus 2 times 50, this statement down here, would be 0. So we would have a box with 0 width, which doesn't make any sense, right? So x has to be less than 50 in order for us to have a box, and it's got to be greater than 0 in order for us to have a box. Okay. Now we're going to come up, what's the formula for volume of a, thank you, volume equals length times width times height. What's my length?
100 minus 2x.
What's my width?
100 minus 2x.
What's my height, Matthew? If you say 100 minus 2x, I'm going to kick you out of class. Our height is x. So you see the method in the madness here. Like like our diagram allows us to come up with those dimensions. And between the two diagrams, and the second diagram, the bottom one, maybe you only need to see it once so you understand where the dimensions go. Now, I don't care if you get the length and width and height right. You could, I don't care, like if you did this in a different order, it's going to be the same thing. But you have to understand where those dimensions come from and what they are. Okay? Now what? Expand. Yeah, expand and simplify, and then take the derivative. Okay, so go ahead and start that. I'm going to do it like this. Negative 2x times negative 2x is 4x squared, but times x is x cubed. Like, I'm going to try to do it in one shot. But if you had to in two, that's fine. But it's probably not that bad. This one to do in two. Negative 200x, negative 200x is negative 400x, but it's going to be x squared because it's times x again. 100 times 100, 10,000. So plus 10,000, 10,000x. Take the derivative. Polynomial again, so v prime at x exists for all x. Yes, you have to say that every time because that's what makes it a complete solution, because maxes or mins can happen when the derivative does not exist. What do they look like when the derivative does not exist? A max or a min? Yeah, but even more, what do they look like exactly? A cusp, right? Otherwise, it's a vertical twist. But a cusp is where the derivative does not exist, but and has a vertical tangent line. Okay, so every single time you have to state that it does not exist. And sometimes there will be places where it does not exist. But if there isn't, if it's just polynomial, you still have to state that. So then v prime at x equals 0 when 12x squared minus 800x plus 10,000 equals 0. Factor that? No, I don't think so. I'm going to use the quadratic formula. I don't know. It doesn't. It does factor. But for something like this, I don't know that it's worth it. I mean, you could common factor and bring your numbers down a little bit. Factor a 4 out of there. B squared minus 4 times . $200 plus 100 is 300 divided by 6 is 50. 200 minus 100 divided by 6 gives me 50 over 3, which is approximately 16.7. Okay, what do you think? We got two answers. Which one's right? How do you know? Why? Because we defined a domain. Isn't that handy? So now we already know which one's inadmissible. In grade 10, it's a tricky thing because it's usually the negative answers that you throw out. But there are a couple of questions where that doesn't happen. Picture frame questions. So same thing here. Sometimes negatives are thrown out because you can't have a negative length. But for us, they'll be outside our domain. But here's the trick in this class for this stuff. When you say something is inadmissible, you have to tell me why. Saying it's outside the domain like that is good enough. If you've defined a domain. If you haven't defined a domain and you say outside domain, I'm going to write on your page what domain. Okay, prediction. I promise you I will. What if you didn't define a domain? You wouldn't know which, but you would probably still figure it out. But what would you say? You would just say inadmissible, then I'm going to say why. So you could say causes one of the dimensions to be 0. Like you could actually give me a description about why it's inadmissible if you'd rather do that. But as long as you've defined a domain, then all you have to say is outside of domain. Does that make sense? Okay. And what were we trying to find here? We were trying to find dimensions of the box of largest value. So height is 50 over 3, and the length equals the width, which equals 100 minus 2 times 50 over 3. Which works out to 200 over 3. Which is approximately 66.7. .7 by 66.7 by 16.7. Any questions about that one? There? So I just did b squared minus 4ac on my calculator and put in the result. Is it centimeters? Oh. .66 meter box. What would you put in that?
Probably wouldn't want to know.
Yeah. Yeah. Okay. One more. Today was 2 boxes in a field. Because this is another box question. But this is a different box question. Example 2 was cutting the corners out of a square to make a box. This one's an open top box with a square base that is being constructed out of some kind of material. So it's different. Okay. Ready to go? So open top box, the square base is have a volume of 2,000. We're not maximizing volume. It gave us the volume. The box is going to be constructed of material that costs $5 per centimeter squared and $12 per centimeter squared for the base. So the sides cost a different amount than the base. Find the dimension of the box that will minimize cost to make the box, and find the minimum cost. Okay, let's draw it. Yes, definitely. Okay. All right. What kind of labels are we putting on this box? Where are we going to put our X? It's a square base box. So if I say this is X, this is also X, this is H, and we're going to figure out H later. Again, if you didn't want to draw the box, you could define your variables with let statements. Let X, or let W for that matter, represent the width of the box. Then the length of the box would also be W. And let H represent the height of the box. You could do that. Okay, next step. You don't have to do these, like the next two steps in order. It doesn't matter to me. But the next one we were saying what is being maximized or minimized. So we're minimizing cost. Which means our function has to be a function of cost. Okay? What are the, what's our domain? What's the restrictions on X and on H? What's the smallest that X can be?
0.
So it's got to be bigger than 0. Yeah, but you're exactly right. Right? So our lower bound is going to be 0. What's our upper bound? Did you have an idea? Yeah. 2,000, good guess. Do you think it's 2,000?
Would it be the root of 2,000 over H?
The root of 2,000 over H. So you're sort of solving something there. Okay, interesting idea.
Or is it just root 2,000 because H has to be a...
Or just root 2,000. Cube root of 2,000? Ibrahim? Why 24,000?
That's the highest cost times.
Oh, interesting idea. Any other ideas? I'm not saying any of them are right or wrong, but it's interesting how there's all these different ideas, isn't there? Monsieur? No, say it, please.
No, it's wrong.
Whoops. Are you sure?
Yeah.
Siri's trying to figure out what the maximum is supposed to be. Nice try, Siri. You're not that smart. Any other ideas? Okay, so root 2,000, that's an interesting idea. Is there an H? So hold on, don't write this down. Volume equals length times width times height. Our length and width are x, so it's x squared times height, which is 2,000. So that's where the square root of 2,000 came from. If I had because then the x value would be 2,000 times h. Or it would be, so what do you think? No matter how big x gets, what if x was 2,000? What's 2,000 squared? Is that 4 million? What value of h can make this equation true? It'd be 1 over 2,000. Okay, let's go bigger. What if x was a billion? Wouldn't there still be an h value that could make this true? So what's our upper bound? There is no upper bound. No matter how big we make the base, we can keep making the height infinitesimally smaller. I don't understand why that's so funny. So our domain is x has to be greater than 0 and h has to be greater than 0. Because for the same reason, no matter what h is, I could just keep making x smaller and smaller and smaller and smaller and smaller. So this one's a little bit different. And some of these questions won't have upper bounds. They only have lower bounds. Okay? All right. Now what? Now we have to come up with our equation. What is our equation going to be? It's going to be a function of cost. So cost, I'll do it right here. Cost equals 12x squared, because the cost of the product for the base, and the base is x squared, is $12. So the 12 comes from here. $12 per centimeter squared for the base. Plus 5 times $5 times x times h but is that it? We only have one base. We have 4 sides. This is surface area. We just found the surface area of the base, and we found the surface area of the sides, and we multiplied it by cost. So x times h is the area of one of the sides, but we have 4 of them, so it's 4xh. And then multiply it by $5 for cost. Does that make sense? Some of these questions say minimize surface area, not minimize cost. So you don't need to do the cost part, you just do the surface area part. But we don't know what h is. So how are we going to figure out what h is? Ooh, interesting idea. We don't have to. You might be able to do it that way, but it would be tricky. We're going to do this. Now I'm going to take that and sub in for h. A little bit of work to clean this up. What kind of function is this? Anybody? Okay. It's rational, right? It's a rational function. It's got an x in the bottom. So it's a rational function. It's not, I could simplify it, get a common denominator. It would look more like the ones we saw in the last unit. But then I would have to use quotient rule, so it's going to be better to leave it like this. Any questions? It's a fairly different setup for this one than the other ones. Okay, we had to come up with an expression for h, come up with an equation for cost. Our first one was in terms of x and h. Sub in for h and simplify. Now I have an equation that models the cost of this. Okay, then what do? Take the derivative. This is 40,000 x to the negative 1. So when I take the derivative, the negative 1 comes out front, makes it negative. And I subtract 1 from the exponent, so it becomes x to the negative 2. This goes back to the denominator. So in one step, I unsimplified, took the derivative, and resimplified. Right? Useful to be able to do that again, saves you a lot of time. Okay. C prime at x does not exist. Or it exists everywhere? Or what? Where does it not exist? Nasir? Huh? At 0. Right. Because if I simplified the derivative, I'd have x squared on the whole bottom. You can't divide by 0. So what do you think about that? Could that be our minimum? What do you think? Not in our domain. So again, you're going to state that, but then you're going to say, whoops, not in domain. And we're done with it. Don't have to do anything else. So I've got 24x minus 40,000 over x squared equals 0. In the last unit, what would you be required to do with this derivative? Simplify fully, right? The whole point is so that we can figure out where it's equal to 0 and where it does not exist. But this is different. In this case, isn't it better to just set it equal to 0? Or I don't know. It's up to you. Maybe you don't think it's easy. You don't think it's better. Maybe you want to get a common denominator, and you can. It's totally fine. But can't I just do that? Set it equal to 0. Move that part to the other side. 24x cubed equals 40,000. X cubed equals 40,000 over 24. X equals the cube root of 40,000 over 24. So that's a little bit different. And sometimes it's going to be more effective. This one could go either way for me, but sometimes it's going to be way more effective not to simplify fully and to just set it equal to 0 and solve it the way it is. There are some other questions that are even more convincing that that's the right thing to do. Okay, and this is about 11.9. So if the width and the length equal 11.9, then the height is 2,000 over 11.9 squared, which is about 14.1. You thought the last box was big. How do you like that one? Okay,